Hi everyone, a warm welcome to the seventh part of problems in wave equation. We got the solution of wave equation as y of xt is equal to sigma n1 to infinity sin n pi x by l an cos n pi ct by l plus bn sin n pi ct by l, where an and bn are calculated by using the equations an equal to 2 by l integral 0 to l fx sin n pi x by l dx, bn is equal to 2 by n pi c integral 0 to l gx sin n pi x by l dx. Really, y of xt is the displacement at any point on the string at a distance x from the origin and at any time t. Next, we have to find y of xt when fx is given or gx is given or both are given. In our problems, fx and gx are either in terms of the trigonometric function sine or polynomials. In the sixth part of problems in wave equation, we solved a problem with its initial velocity is given as a polynomial. In this video, I am going to solve a problem in which its initial velocity gx is given as a trigonometric function. Let me illustrate it.
Look at the question. A string of length L is initially in the equilibrium position and each of its points is given the velocity y equal to v0 sin cube by x by l. Determine the displacement. Say our wave equation is dou square y by dou t square is equal to c square dou square y by dou x square. See, from the question it's clear that length of the string is L. So we can write the boundary conditions y of 0 t equal to 0 and y of L t equal to 0 for every t. Next, we have to write the initial conditions. See, in the question it is given, the string is initially in the equilibrium position. Equilibrium position is, say the string is like this. So, fx, its position is 0. It is on the x-axis in the equilibrium position. See, on the x-axis, x is 0. So, fx is 0. That is y of x0 equal to fx, which is 0. Next, regarding initial velocity, that is dou y by dou t at t equal to 0. See, it is given that initially it is given by a velocity y is equal to v0 sin cube by x by l. See, this is our initial velocity, that is g of x. We have to find the displacement, that is the displacement at any point on the string. We know the solution of the wave equation is y of xt is equal to c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt. That is equation number 1. We have to substitute these conditions one by one in equation number 1. Consider equation A. So you have to write y of 0t. For that you put x equal to 0. You can see x in cos px and in sin px. There you put x equal to 0. You can see it is c1. This term is 1 and this term will be 0. So c1 into 1, which is c1 into 0. Then c3 cos cpt plus c4 sin cpt. Given y0t equal to 0, which implies this equal to 0, which implies c1 equal to 0. So you put in equation number 1. So we have y of xt is equal to c2 sin px into c3 cos cpt plus c4 sin cpt. That is the modified solution of the wave equation by applying the condition A. Next, we have to apply the condition B. So here the condition B is y of lt equal to 0. So we have to find y of lt. So in equation number 2, you put x equal to t. So in equation number 2, you can see x is only in sin px. So here you replace x by L. So it is C2 sin PL, C3 cos CPT plus C4 sin CPT. See, condition B is y of L equal to 0. That is C2 sin PL into C3 cos CPT plus C4 sin, which implies C2 sin PL equal to 0. This implies sin PL equal to 0 because C2 cannot be 0. If C2 is 0, from the equation 2 it is clear y of xt is 0. That is not possible. So C2 cannot be 0. So we have sin PL equal to 0, which implies PL equal to n pi for n equal to 0, 1, 2, 3, etc. You put, that is P equal to n pi by n. You put in equation number 2. You put in equation number 2. See, this is our equation number 2. So we have y of xt is equal to C2 sin n pi x by L, C3 cos c n pi x by L t plus C4 sin c n pi x by L t. You just put p equal to n pi by L. Say this is for n equal to 0, 1, 2, 3, etc. And also, when n is 0, you can see y of xt will be completely 0, which is impossible. So we have to avoid the value for n equal to 0. So here this solution is true for n is equal to 1, 2, 3, 4, etc. By considering all these solutions, you can write its most general form of the solution, and it is given by sigma n1 to infinity. You consider C2 into C3. It's an arbitrary constant. See here sin n pi x by L is a common term. C2, C3 is an arbitrary constant and it depends on n, so we can denote it by an cos c n pi x by L t plus. Similarly, C2 into C4 is another arbitrary constant and also which depends on n, so we can denote it by Bn, and Bn is sin c n pi x by L. See, this is the most general form of the displacement of our string. Next, we have to find An and Bn. An is 2 by L integral 0 to L fx sin n pi x by L dx. Bn is 2 by n pi c integral 0 to L gx. Same trigonometric function sin n pi x by L dx. Here, fx is 0. So what is An? An equal to 0. Next, we have to find Bn. Since dx is b0 sin cube pi x by L, see it is in terms of the trigonometric function sin. As I mentioned in previous videos, if fx or gx is in terms of the trigonometric function sin, then you can find An or Bn without using these equations. So here you can find Bn without integrating. See, for getting Bn we have to use this condition, that is dou y by dou t at t equal to 0 is b0 sin cube pi x by L. So for the convenience, we got An equal to 0. So what is y of xt? Y of xt is equal to sigma n1 to infinity. You put An equal to 0. So this term is 0. So we have Bn sin n pi x by L sin n pi ct by L. For applying this condition, you find dou y by dou t. What is dou y by dou t? Sigma n1 to infinity. Here we have to differentiate with respect to t. So you can see the variable t in this term only. So you have to differentiate this term only. So while differentiating y partially with respect to x, you have to keep x as a constant. So its derivative is bn sine n pi x by l into derivative sign is cos, that is cos n pi c t by l into n pi c by l. So this is dou y by dou t. Next we have to write dou y by dou t at t equal to 0. You put t equal to 0 on the right side. In the right side you can see t only here. So there you put t equal to 0. So this term will be 1. So it is bn sin n pi x by l into n pi c by l. Given dou y by dou t at t equal to 0 is v0 sin cube pi x by l is equal to sigma n1 to infinity n pi c by l bn sin n pi x by. For avoiding the confusion between this angle and this constant, you take this constant in front of this term. See, the right side is in terms of sign with the power 1. See, all the sign terms are linear. Here the sign term is with the degree 3. So we have to replace sin cube by x by l in terms of linear functions. For that we have to apply the result for sin cube theta. What is sin cube theta? For writing sin cube theta, you write sin 3 theta. We are familiar with this equation. Sin 3 theta is 3 sin theta minus 4 sin cube theta. From this sin cube theta is, you take 4 sin cube theta to the left side and you take sin 3 theta to the right side. You can see sin cube theta is 1 by 4, 3 sin theta minus sin 3 theta. So this implies v0 into 1 by 4 is a constant, 3 sin pi x by l minus sin 3 pi x by l is equal to, you expand the summation, when n is 1, pi c by l b1 sin pi x by l plus when n is 2, 2 pi c by l b2 sin 2 pi x by l. See, in the left side you can see a term sin 3 pi x by l. So you have to expand the right side up to n equal to 3 plus 3 pi c by l b3 sin 3 pi x by l plus etc. Next you equate the corresponding terms in both sides. You can see you equate the coefficient of sin pi x by l on both sides. The left side, v0 by 4 into 3 is equal to pi c b1 by l. Right? So what is b1? Here we have to find bn. bn for n equal to 1, 2, 3, 4, etc. See, our aim is to find b1, b2, b3, etc. By equating corresponding terms on both sides, we can find what is b1, b2, b3, etc. See, from this equation, we have b1 is, what is b1? 3b0 l by 4 pi c. Next, you equate coefficient of sin 3 pi x by l on both sides. You can see the left side is minus v0 by 4 is equal to, on the right side, sin 3 pi x by l. See this, and its coefficient is 3 pi c b3 by l, which implies b3 is equal to, what is b3? Minus v0 l by 12 pi c. So we have b1 equal to 3b0 l by 4 pi c and b3 is this one, See, next to B2. See on the right side, there are infinitely many terms with the B1, B2, B3, B4, etc. But on the left side, you can see only two terms. Sin pi x by L. That is the you can equate that term with the right side. Next you have one more term in the left side. You equate the corresponding terms on both sides, we get B3. So by equating, we will have only B1 and B3. And what about B2, B4, B5, B6, etc.? There is no such terms on the left side. By equating on both sides, you can see B2, B4, B5, etc. equal to 0. So now we have the values of BI's. So what is y of xt? See, from this it's clear we have only two BI's with non-zero values, only B1 and B3, and all other BI's are zeros. So what is y of xt? You expand this. B1, see y of xt is B1 sin pi x by L into sin pi ct by L plus B2 sin 2 pi x by L sin 2 pi ct by L plus B3 sin 3 pi x by L sin 3 pi ct by L plus etc. See, this is y of xt. See, this you have to put B1, B2, B3, etc. See, B1 is 3b0 L by 4 pi c into sin pi x by L sin pi ct by L. B2 is 0. B3 is minus b0 L by 12 pi c sin 3 pi x by L sin 3 pi ct by L plus all other terms are zeros. So this is the required displacement at any point on the string. Let me answer one more question. Consider the question. Write the boundary conditions and initial conditions of a string of length L is initially at rest in equilibrium position, and each of its point is given an initial velocity v0 sin pi x by L for 0 less than x less than L. See, in this question, you have to write only its boundary and initial conditions. You can expect such questions only for 3 marks. See, in this question, there is no need of solving. See, here we have to write its boundary conditions and initial conditions. From the question is clear, length of the string is L. So, its boundary conditions are y of 0t equal to 0 and y of ft equal to 0. These two conditions for any time, that is for everything. Next we have to write its initial conditions. See, in the question, it is given that the string is initially in equilibrium position. That means fx is 0. So y of x0 is equal to fx and it is 0. Next initial condition is based on the initial velocity and it is, that is dou y by dou t at t equal to 0 is g of x and it is given by b0 sin pi x by L for 0 less than x less than L. See, these two are our initial conditions. So these are the boundary conditions and initial conditions. So in this question, only we have to write the boundary conditions and initial conditions. If you wish to find the displacement at any point on the string, you consider the solution of the wave equation and you substitute these 4 conditions in that solution as mentioned in the previous question. See, in the previous question, gx is v0 sin q pi x by L. See here, Gx is v0 sin pi x by L. This question is more easier than the previous question, so you can do it.